Hello chemists, we're going to go over the Unit 3 lab part 1, chemical bonds and the periodic table. You should have a lab sheet that looks something like this. Please make sure you're writing your answers on your lab sheet. You won't get any credit because it won't save for the software, which you'll find right here. You'll have to go to the chemistry bar on the software page, and then you want to click chemical bonds. Don't worry if you can't get the software to work. We'll go over everything you need to know in this video. So let's begin. I'm going to fire up the software. It'll look something like this, and we'll start at page 1. So here's the first part of the lab. We're going to learn about representations of electrons in orbitals. Electrons are key to forming two broad categories of chemical bonds, covalent and ionic. Atoms, which have a nucleus surrounded by electrons, are represented in several different ways. Here's an s orbital. You might be familiar with the s orbital from the Unit 2 lab. Here's a p orbital, and you may also be familiar with that. You can see how the shapes of orbitals are derived from the probability map. We talked about probability maps in the Unit 2 lab, where you can see this sort of cloud of electrons is denser near the nucleus and less dense on the outside. So that probability map forms sort of a circle here, and that's what the s orbital is representing. Same with the p orbital. The atoms are probably going to be in these two clouds over here, and so they're represented in a p orbital map that looks like this. So, which answer best describes electrons when they surround the nucleus of the atom? This question is number 1 on your lab sheet. Please highlight the best answer. Now we're going to talk about orbital shapes, or distorting those orbital shapes with an electric charge. We're asking the big question, how are electrons, which are negatively charged, affected by the presence of other charges? Let's find out. I'll click to activate this and I'll show you. So we can use this simulation to answer question 2, 3, and 4 on your lab sheet. Let's apply an electric field to the box first. As we charge one of the walls here, you can notice, keep your eye on the probability map of the electron cloud here. Notice how that shifts. The negative here and the negative electrons, they repel each other. Let's give the right wall a charge. And that even pulls out the orbital more, as the negative electrons are attracted to the positive side of the wall here. Let's switch sides just to see if things are gonna... That goes back, it's attracted to both sides now, so the orbital sort of returns to its original shape. Let's make the other wall negative. And again, the negative electrons are attracted to the positive charges over here and repelled by the negative charges over here. So that's number 2. Let's use a point charge here. This is basically just a positive charge, and let's notice how that distorts the probability map of where the electrons are. As we bring it closer and closer, the electrons head for that other proton. They're also attracted to this one, but they're attracted to this one as well, and that distorts the shape of the orbital, or the probability map in this case. Now let's use another hydrogen atom and see what happens when we bring them together. You can see that they start to get distorted even when they come a little bit close together, because the electrons here are reaching over for this positive charge, and the electrons here are reaching over for this positive charge. If we bring them close enough together, you can see that there's kind of a bright blue spot in the middle, and that's showing where electrons are shared. An electron for this atom might come over here and spend a little bit of time over here, but then head back over here. And so that idea of sharing is called covalent bonding, and we'll explore that a little bit later in the lab. So you should be able to answer number 2, 3, and 4 at this point. So we've already looked at what a covalent bond looks like in terms of the probability map. How are electrons involved in the formation of a covalent bond? That's the big question we're looking at here. We've already had the opportunity to answer question 4. Now let's talk about question 5. A covalent bond is formed when electrons from 2 different atoms are considered to be shared between the nuclei. Remember that bright spot between the 2 hydrogens? Move the 2 hydrogens atoms close together and explain how this can be a representation of a covalent bond. I'll leave that up to you. You've already seen it and you have a screenshot on your lab. So here's that screenshot of the covalent bond. If you need to reference that, it's page 3 of your lab sheet. And here's question 4, showing them coming together here. Here's question 5. And we're headed towards question 6. Where do the electrons end up? And we'll talk about that in the next section. So this section and a lot of the rest of the lab is going to be about sharing. How well atoms share electrons. Different kinds of atoms are better than others at attracting electrons to themselves once they have bonded with another atom. How can we represent the degree to which atoms in a bond share electrons evenly? So here's a way of showing something that's shared evenly. And then we can get to a place where we show charges using this scale here, where a negative charge or the presence of more electrons, or an area where electrons hang out more frequently, we're probably going to see more electrons, is blue, and an area where there's sort of a lack of electrons or there is a lower probability of finding an electron, we'll color those red. So you'll see there's a way of showing that this atom probably hogs the electrons. The electrons spend more time on this side of the bond. So let's go to the next page and we'll start experimenting. We're going to look at something called electronegativity and how that affects the location of the electrons. I'll activate this and we'll be able to answer this question. So if you remember, electronegativity is how well an atom can pull electrons towards itself. A high electronegativity means it's good at pulling electrons. A low electronegativity means it's not so good at pulling electrons away from other atoms. Right now, the electronegativity is set the same, so there's no charge here. They're even. This would be known as a covalent bond. Let's bump up the difference here. Oh, there's a significant difference here. Look at these numbers. This is a very low electronegativity, and this is a very high electronegativity. You can see that this has a negative charge. This blue part is a negative charge, which means the electrons are more likely to be over here than they are to be over here, which has the positive charge. So as we kind of mess with this electronegativity, you can see that the charges adjust. If the electronegativities are closer, these colors are less bright, and that represents less polarity in the bond. If we bring them back to the middle so that they're same, or anywhere where the numbers are pretty much the same, it goes white because there's no difference in electronegativity, so they have to share equally. So now you can answer question number 6. Now you should be able to answer question 6, question 7, and question 8 on your lab. Make sure you explain your answers to the 2 multiple choice questions here. Now we're going to explore how electronegativity of each atom affects the type of bond that will form between the 2 atoms. Because electronegativity difference determines the bond type. As we can see, we get our same animation here, but they've added a scale to calculate the difference in the electronegativity in the two atoms and to indicate with the green arrow what type of bond will form. We're going to experiment with making different kinds of bonds and then answering the following questions, which will also be on your lab sheet. So you can see that we have our same electronegativity sort of monitor here, but now we have a wedge that tells us what kind of bond we're forming. If we have very even electronegativities, you can see that our green indicator here is under the nonpolar covalent bond. In other words, they're sharing equally. If we make electronegativities very different, really stretch that out, we're making an ionic bond. So there's a high difference in electronegativity in an ionic bond. They don't share well. And now we're asking the question, well, what about the medium area? If they sort of have a medium difference in electronegativity. We'll bring things a little bit more close to the middle here. If there's a medium difference in electronegativity, it's called a polar covalent bond. They share, but they don't share well. They don't share equally. You can see that there is indeed a charge here and a charge here. This is where you're probably going to find more electrons than over here. So this is negative and this is positive. Let's make it an ionic bond again, make a really big difference. And you can see there's a difference, there's a very big difference in charge as well. In an ionic bond, it's very negative over here and very positive over here, and that has to do with the difference in electronegativity here. So for questions 9, 10, and 11, you have some screenshots that'll help you make some decisions. Remember to look at the difference in electronegativity, whether it's low, medium, or high. And they'll give you a hint of if you want to make a nonpolar covalent bond, an ionic bond, or a polar covalent bond. Question 12 and question 13 on your lab sheet ask about the approximate numeric difference in electronegativity. That, in other words, take the electronegativity of one atom and subtract it from the other and look at that difference in electronegativity and how that difference relates to what kind of bond you're forming. For example, you could go up here to an ionic bond and look at 339 minus 0.97, which is going to give you about 242, I believe. So that difference of 242 kind of leaves you in the ionic range. If you look at the difference of 0.07 here, that puts you in the non-polar covalent range. So think about those differences and kind of in your mind trying to make some boundaries of where covalent, polar covalent, and ionic are. In this section, we're going to get real. In other words, we're going to use real atoms from the periodic table now. We're going to ask ourselves what kind of bonds would form between those real atoms on the periodic table. We're going to look at real pairs of atoms and look at the differences in electronegativity and hypothesize and examine what kind of bonds form between real atoms. We're going to look at the difference between sodium and chlorine, between hydrogen and oxygen, and between carbon and carbon. To look at the difference between sodium and chloride, I've already dialed in the electronegativity for sodium. We can find the electronegativity for chloride, just like I did for sodium, by clicking on this gray ball here, looking at chloride, and this here is a periodic table of electronegativity. So you can see that chlorine has a really high electronegativity here, and sodium is all the way over here with a low electronegativity. So I'll click on chlorine to get that electronegativity to show up. And now you see there's a pretty big difference in electronegativity, 0.93, 3.16. That puts us in the ionic range here. So for the difference between sodium and chloride, or chlorine, excuse me, make sure that you put ionic. So we just answered number 14. We're going to look at questions 15 and 16 as well. The next bond is between hydrogen, I'll dial up hydrogen here, and oxygen. And so you can see the difference in electronegativity here kind of falls in the medium range. And the medium difference in electronegativity means there is sharing, but it's not equal, and that would be polar covalent. So sharing but not sharing equally, kind of a medium difference in electronegativity, that's polar covalent. The next bond we're going to look at is between carbon and carbon. So I'll click here, I'll bring up a carbon atom, and I'll bring exactly the same atom here. And since they have the same, exactly the same electronegativity here, the difference is almost nothing, and you have a non-polar covalent bond. They're sharing perfectly equally because they have exactly the same electronegativity here. And that's great for biology because there are a lot of carbon-carbon bonds in biology, and we need those bonds to be covalent and not polar. You can see the bond here. There's no charge in the bond. So the last question in this section asks, experiment with choosing various pairs of elements from different sides of the periodic table to see what kinds of bonds are formed. What patterns do you see? So we'll do a little experimentation here. So let's choose another equal sort of bond where we choose exactly the same atoms. A lot of times you'll see oxygen and oxygen bonded. And again, when there's no difference, you see a nice non-polar covalent. How about carbon and oxygen? That's pretty common in biology. That's going on in you right now. That's kind of getting towards the medium range of polar covalent, of electronegativity difference into the polar covalent range. And you can see that the oxygen here is negatively charged, and that happens very often in any bond where oxygen and carbon bond. Oxygen tends to be more negative and tends to be polar, and that governs a lot of biology. You know that water is polar because oxygen hogs the electrons away from hydrogen in water, and it does it in a lot of other biological molecules as well. But let's focus on some places where there are a lot of difference on the periodic table. So let's click here, and let's click on potassium. I'm a little bit biologically inclined here. Potassium is an important electrolyte. And let's go with potassium chloride. So far left on the periodic table, far right, there's a big difference here, and we're in the ionic range. Let's go back to the periodic table and pick something that are a little bit closer, like carbon and nitrogen. They're got a little bit of a charge difference. They're kind of right on the borderline between nonpolar covalent and polar covalent. They're right next to each other on the periodic table. Let's try something that's a little bit closer. Let's try a boron and an oxygen. They kind of got a medium electronegativity. They're not right next to each other on the periodic table. They've got a little bit more distance, a little bit more difference in electronegativity, and they kind of fall in that polar covalent. Let's do one more to kind of illustrate a point. If I choose something from the far left, like calcium, and then I go over to the far right, I pretty consistently get an ionic bond. So you should be able to make some conclusions from the screenshots you've got and the experimentation we've done here. So for question 17 on your lab sheet, in addition to the experimentation we just did, I gave you some screenshots to help see some patterns as well. In this section, we're going to continue to talk about the difference in electronegativity and how that allows us to predict the type of bond that will form between two atoms. And look, hey, there's a chart. If the difference is less than 0.5, it's a nonpolar covalent bond. 0.5 to 2.1 is polar covalent, and more than 2.1 is ionic. So if we look at the difference here between carbon and carbon, carbon is exactly the same. There's no difference. It's less than 0.5, so it's nonpolar covalent. That makes sense, I hope. The the difference between hydrogen and oxygen is 1.34, and that falls in the middle between 0.5 and 2.1, and so that's a polar covalent bond. We've seen this table before. We can see that there are trends in electronegativity. The most electronegative atom is here. Fluorine likes to hold on to its electrons the most. It's kind of it's the naughtiest atom, and you can think of a naughty word that starts with F probably. So that might help you remember this is kind of the naughtiest atom. It's the grabbiest atom. It'll steal your electrons if you're not looking. So we've looked at these trends, and now you should be able to predict based on the electronegativities from the periodic table here. You can look at the differences, and then you can look at the chart and figure out what kind of bond is it. So for example, between carbon and oxygen here, let's scroll up and look at carbon is 2.55 and oxygen is 3.44. So that that's a difference in the 0.9 range. So let's go back up to our table at the top here and look at where that 0.9 range puts us in terms of bonds. Well, 0.9 is between 0.5 and 2.1, so the carbon-oxygen bond is going to be polar covalent. Remember, to get the difference in electronegativity, you find the electronegativity of both atoms in this periodic table. So carbon was 2.55, 3.44 minus 2.55 is about 0.9 something. So now that you know how to subtract the two electronegativities that you find on this periodic table and put that difference that you find in this table and figure out what kind of bond it is, you should be able to answer questions 18, 19, and 20. So now we get to look at larger molecules. Polarity of a single bond within a larger molecule can make the entire molecule polar or nonpolar, which is especially important in biology. By studying how pairs of atoms bond together, it can help you design more complex molecules with specific properties, like drugs. Drugs are designed to work within the human body in both polar and nonpolar regions, and so they need to be designed to in particular ways, in particular shapes, and those shapes depend on whether they're polar or not. So there's a lot going on in pharmaceutical design, and you need to know about charged atoms. If we look at pentane and one pentanol, we see that one pentanol has an oxygen here, a carbon-oxygen and an oxygen-hydrogen bond, and it ends up being charged on the end with the oxygen. Here, pentane is a little bit charged here and there, but since it doesn't have an oxygen, it's largely uncharged. Let's go down a little bit. So in order to make some predictions, we can use our periodic table of electronegativity again. Let's look at a couple of large molecules that happen to be amino acids. If you remember from biology, the amino acids form or bond together in very particular sequences, and whether they're polar or nonpolar, whether an amino acid is polar or nonpolar, affects the shape of the protein. So we're trying to decide whether these two amino acids are going to be polar or nonpolar. If you notice, glutamine right here has an oxygen-carbon bond. That oxygen-carbon bond is a lot like this oxygen-carbon bond. It's not a double bond like it is below, but it's going to have similar effects on the polarity. Here, phenylalanine has no oxygen, and all those are carbon-carbon bonds. Just like pentane here, all the carbon-carbon bonds are not polar. So you might be able to make some predictions about which one of these is polar. And that's exactly what you're asked to do. On your lab sheet, question 21 asks you which amino acid below would have a more polar side chain. Look carefully for which one has oxygen. And then question 22 asks you which one's going to be nonpolar to work well in a cell membrane. So you can figure out which one doesn't have oxygen and which one's going to work well in a cell membrane. And question 23, you can explain your choice in question 21. So we're on the last page here of the sim. There are some summary questions. You can see here that they're just multiple choice questions. There's nothing that can be manipulated. It's just pictures. You have all of those pictures on your web sheet or your lab sheet, and you should be able to answer the rest of the questions on your own. Thanks so much. Make sure you've answered all the questions on your lab sheet before you turn it in. And if you're writing free response answers, make sure they're in another color so they're easy to grade. Thanks so much. This is Miss R signing off.